Greetings and welcome, friends. Mr. Waddy here. We are talking about section 4.5, dilations, which I think I would be found correct if you investigate, is the first type of transformation we've talked about, which is not rigid. This will not result in a congruent figure, but similarities abound, my friends. Similarities. Especially if you listen to tomorrow's lesson, which is in the future, assuming we all make it, and a video is posted online. Similarities abound. Here we go. So a dilation is a transformation in which a figure is enlarged or reduced with respect to a fixed point C called the center of dilation. Ooh, right there. Right there. Yep. Center of dilation. And a scale factor K, which is the ratio of the lengths of the corresponding sides of the image and pre-image. Okay. All right, so we can see that K here is the ratio of like PR to P prime, R prime, or vice versa, I guess. Yeah, it'd be it would be the image over the pre-image. So that's the ratio. A dilation with center of dilation C and scale factor K maps every point P in a figure to point P prime so that the following conditions are true. If P is the center point C, then P is equal to P prime. So basically, if I was dilating and my center was right there, right, my figure gets larger, but that particular point stays exactly the same. And you guys experimented that in Geometry Sketchpad moments ago when I asked you to drag the origin onto one of your original triangular points. Agreed, yes. If P is not the center point C, then the image point P prime lies on CP, the ray, and the scale factor K is a positive number such that K, let's see, that's a sad K right there, is equal to CP prime over CP. And then here's the fact. I think I tricked some of you guys on this one. Angle measures are preserved. So you do not multiply the angle measures by K. The angles are congruent, but the side lengths have been scaled up by the factor of K. All right. However, it's not always scaling up, as one might suspect. Whoa, let's see. My mouse was freaking out. Let's see. A dilation is a reduction when the value of K is between 0 and 1, and a dilation is an enlargement when K is greater than 1. That's just fractions, friends. That's how fractions behave. I think you guys would agree. Multiplying by a fraction that is larger than 1 in that sort would do that. So let's see. Identifying dilations. Example 1. Find the scale factor. Question? No? Comment? No? All right. I thought someone was said. I got all excited. I was hoping for some interaction that was not merely in my comments. Yes, question. Naranja, which actually is Spanish for the fruit, but is, side question, all right, right back at you. Is naranja also the word for orange, the color in Spanish? No. I can't remember. I don't remember. But anyways, that's a question for the internet or someone who speaks Spanish. Let's see. Find the scale factor of the dilation. Tell whether the dilation is a reduction or enlargement. What are your guys' thoughts for A here? A. Okay, it looks like it's going from P to P prime. P prime looks larger, so I would call that an enlargement. Right? And does anyone have a suspicion regarding the scale factor? Let's see, K is going to equal 12 to 8 is the ratio. 4 goes into both of those. 3 times for the numerator and twice for the denominator. So K is equal to a 3 to 2 ratio or a scale factor of 1.5. All right, so yeah. That's how that works. I like it. I like it. Notice we actually don't know the dimensions of the the original here. And that's okay. Let's see, for B, there's the p to the p prime. Right? So it looks like p prime is smaller. So we would call that a reduction. Nothing too complicated here, friends. And let's see, the value of k is going to equal 18 to 30, right? Because it's the image over the pre-image. And also, the fact that I knew this was a reduction, I would have expected the numerator to be smaller than the denominator in order for that to happen. Both of those can be reduced by 6. 6 goes into 18 3 times and into 30 5 times. So k is a 3 to 5 ratio for the scale factor, which, by the way, I believe is equal to 0.6. So linearly, it is 60% of the original values. Right. Ooh, guys, here we go. Coordinates rules for dilations. And this is where, remember, well, actually, in future generations, I probably won't teach that problem until this part here. But remember when we had to, like, move point P amongst a directed segment and all that, and that was a crazy problem that took like 15 minutes every time? This is where it is actually somewhat helpful. Finally. Coordinate rule for dilations. If point P is x comma y and is the pre-image of a point, then its image after a dilation centered at origin 0, 0 with scale factor k is the point P prime where I multiply each of those by k. So if k is bigger than 1, P prime will be out here. If k is less than 1, like 0.8 or something to that effect, then my new P prime would be right 80% of the way towards that. And the way this works, I do want to point out, I do want to, right? Here is the x dimension. Here is the y dimension, like so. And notice that this distance, no, I missed it. This distance right here would be k times x, and this distance would be k times y. All right, so the diagonal is going to be k times larger, as well as the horizontal and vertical components for their coordinates. So interesting results, perhaps predictable. I don't know. Did you guys see that coming? Yes, maybe so. Let's see. Here we go. All right. Example 2, dilating a figure in the coordinate plane. Graph triangle abaca. Here we go. I can't wait. It's going to be great. I can do this part. I'm going to get all the partial credit. Let's see. A is at 2, 1. There is my A. B is at 4, 1. B right there. And C is at 4, -1. There is point C. And I don't know, that's like a triangle or something. And it asks me to find its image after a dilation with a scale factor of 2. And it didn't say about which point, but what point do you suspect they want us to do this? Yeah, probably the origin, right? It doesn't say origin up here anywhere, right? No, so it's just assumed. Yeah, so that's what we'd have to be aware of there. So yeah, those were actually pretty good lines I just drew there too. So what we can do for A prime, we'll do this the proper way, using the property we just had. A prime is going to be 2 times 2, 2 times 1, which is going to be the same as, I don't know if equal signs are even appropriate. I'll just write it this way. Yeah, that's better. Which is the same as 4, 2. All right, so let's see. Over 4 up 2, there is my A prime. B prime. B was 4, 1, so I'm going to multiply 2 times 4 and 2 times 1. and that will become 8, comma 2. And so let's see, that's not going to fool me this time. 2 less than 10 is 8, and here is my 2 for my B primes. Right? And C prime, as you guys can guess, I will just multiply its coordinates by 2, and even with this -1, it will still behave properly. So I'll have 8, comma -2. So there we go, there's C prime. What do you know? And if I draw, let's draw some of these lines here. Notice how wonderful they scale up. Look at that. And one of those. And one of those. Would you look at that? Would you look at it though? Thing of beauty. So let's see. So this was scaled up by a factor of 2. And then let me ask you a question. We talked about this with Geometry Sketchpad earlier. In terms of area, what multiple larger is A prime, B prime, C prime? It is 4 times larger in terms of area. It is only 2 times larger in terms of its linear dimensions. Okay, so interesting stuff. We'll talk about that in future geometry. Yes, Josh. Well, to find that out, what happens is if it's a scale factor of 2 for the linear dimensions, the area is whatever that scale factor is squared. So 2 squared was 4. If I wanted volume, 9, exactly, 9 times the area. If I was talking about volume for a 3-dimensional object and scale factor was 2, the volume would be 2 cubed as much. So it would be 8 times greater when the scale factor was 2 for the linear dimensions. But really, I mean, I didn't mean to spoil the rest of geometry for you. If only that was the last thing we had to learn in geometry. Well, what do I mean, if only? Aren't we glad that geometry just, there's like more to learn? There's an adventure here, guys. We're exploring. We're geometric pioneers. This is amazing. Let's see. Example 3, dilating a figure in the coordinate plane. Graph quadrilateral kilomenon with vertices as such. Okay, we're getting good at the graphing, friends. Let's see, -3, 6. So -3, up 6. There is K. Hip hooray. Let's see, L is 0, 6. L, and M is 3 with the 3. M. Oh, that was like, there we go. And N is -3 with the -3. So hopefully you guys can catch up. Well, you guys are still plotting. I'll just draw some lines with my straight edge. Oh, that wasn't quite right, but that's fine. Close enough. Here we go. And this time we're going to have a scale factor that is between 0 and 1. So we're going to have an image that is smaller than the pre-image. Right, so there's my original. Okay, scale factor K is 1 to 3. All right, let's deal with a few of these points and see what happens. Maybe we won't do all of them. So if I want to find K prime, it will be 1/3 of -3, comma 1/3 of 6. Hey, how convenient of them to have given us all coordinates that were divisible by 3. So let's see. So this would be -1, 2. So -1, 2, right there, K prime. Right? Let's see. L prime will be 1/3 times 0 and 1/3 times 6. So that's just going to be 1/3 of 0 is 0, friends. Yeah, ain't nothing more than that. That'll be 0, 2. L prime. let's see, let me just third these other values for sake of time. A third of 3 is 1, a third of 3 is 1, so m prime is going to be a 1, 1 with m primes at. And a third of negative 3 is negative 1, and same over there, so negative 1 for n prime. So, let's see. I'll just hand draw those lines till it looks good. Something like that. Bam. So there's my new shape. It's linearly 1/3 the size of the pre-image. Area-wise, it is 1/9. Actually, that would kind of be a fun activity to like turn this into a puzzle and see if I could fit 9 of those little yellow ones inside of the green one. Yeah, we won't take the time to do that, but it could happen, friends. It could happen. So let's see. Yeah, that I feel like I was going to say some more after that. Notice that where n prime was 1/3 of the length along the line. Yeah, maybe I'll do that. I think that's a little bit interesting anyway, worth pointing out. Let's see, so if I have that there, notice that this diagonal dimension, that k prime is 1/3 of the way to k. All right, you guys see that? Does that make sense? So even the diagonals, not just the regular coordinates, are thirded, so to speak. So yeah, from m to m prime is 1/3 of the way. Look at these. Yeah, m prime is a perfect example. One diagonal compared to 1, 2, 3 diagonals right there. That just makes sense, friends. That don't just make sense. All right, let's see. How am I doing? I've got a construction in there, but we'll talk about that later. Negative scale factors. Yeah, I guess I should show you that. We'll read this. In a coordinate plane, if you have a negative scale factor, things still happen. Yeah. You can have scale factors that are negative numbers. Hip hooray. Doop-a-doo. When this occurs, the figure rotates 180 degrees so that when k is greater than, wait a minute. All right, okay. So when k is greater than 0, a dilation with a scale factor of negative k is the same as the composition of a dilation with a scale factor of k followed by a rotation of 180 degrees about the center of dilation. So yeah, notice, if I scaled this orange image up to k, that's what it would look like. Negative k is the same size as that, but it done be rotated 180 degrees. Actually, we'll rotate it that way for funsies, right, if I was to do that. Okay, so that's the idea. Yeah, notice that, yeah, it's a rotation, not a reflection about the line. That would be perpendicular to those other ones. And yeah, the same thing. Yeah, good stuff. Good stuff. Yeah, let's see. So, yeah, using the coordinate rules for a dilation and a rotation of 180 degrees, you can think of the notation as this. But yeah, we're good. We know that. We get that. So let's do example 4. Ooh, let me hit some enter button a couple times here. There we go. Example 4, follow along. Look at me, I'm singing a song. Yeah, sorry if you're arachnophobic. Also, I'm sorry if you are apeirophobic, such as my wife. Apeirophobia is the fear of infinity, or just big numbers. Yeah. So her being married to a mathematician, she freaks out whenever I talk about large numbers or infinity. Ooh, boy, yeah, yikes. And sometimes I mention infinity in my sermons, and then that's just like, man, I wasn't supposed to feel uncomfortable in church, right? Let's see, triangle FGH with vertices F, G, and H, and its image after a dilation of, with a scale factor of -1/2. All right, let's see how quick I can plot these points. You guys are expert plotters now. -4, -2, right there with point F. Like so, G is -2 up 4, G, and H is -2, -2 with the H there represent. So a scale factor of -1/2, let's see how quick I can do this. So F prime is going to be a negative a half of those values. So negative a half times negative 4 for the new x coordinate, and negative a half times negative 2 for the new y coordinate is just going to become positive 2, positive 1. That's crazy. Sorry. I've got actually perfect example of dilation and scale factor. For my wireless writing tablet, I make the writing area quite small. So instead of me, if like I was on the board writing and I have to move my hand like 3 feet across to like draw a long line, I only have to move my hand like 2 inches, you know, to scale it up to like the 10-foot wide projection screen that we have. So like when I do this, I actually almost never have to pick my hand up to move from one end of the screen to the other, versus like if I use the full size of the space, you know, then I'd have to like keep picking up my hand to move it around. So in terms of speed, you're exactly right. I can be speedy because I've made a small area represent a large area on my screen. So let's see. So here's my f prime. It's at 2, 1. Which notice, if I was to draw the line through the center of dilation, if I could do that. No, that's not even close. That one was closer. Right? That it's actually just in the opposite direction. Right? So here's 4 units this way, or diagonal-ish ones, and here's 2 that way. So yeah, so you can kind of see how that makes sense. So let's see. I'll quickly do these other ones. So G prime is going to be negative a half. Actually, no. Let's just write it. Negative a half times negative 2 is positive 1. Negative a half times 4 is going to be negative 2. So my G prime is at 1, negative 2. G prime all the time. G prime. Also here was my F prime. And H prime represent negative half of both of those will be at 1, 1. H prime. So yeah, so I get a right triangle that is smaller and is in the opposite direction because of the negative. And you can see that it's kind of like a 180-degree rotation if I was to scale down and then rotate. Question. It equated, here we go, this to, let's see. It equated this to scaling it by a factor of k followed by a rotation. If I rotated and then scale factored, do you think I would have ended up with the same thing? Is that composition, is that associative? Yeah. If I rotated the little guy and had this, and then scale factored up by k, would that have been the same thing? Yes. All right. That's my sad sketch of a justification. But yeah, it would work out. So I could rotate and then scale factor, or I could scale and then rotate. It don't matter, not one bit. All right, let's see. Are we going to do the spider problem? Is that one? That's
a phobia.
A phobia? All right. Well, then let's just do the photograph. Finding a scale factor. Here we go. Why can't we what? I still couldn't hear you. I'm sorry. Oh, the spider one? Well, you heard it. People are scared of spiders, man.
Gosh,
We do math with I'm more scared of that.
Okay. So, all right, here we go. You are making your own photo stickers. Your photo is 4 inches by 4 inches, denoted there. The image on the stickers is 1.1 by 1.1. What is the scale factor of the dilation? What's k going to equal, friends?
Whatever.
Which way do I do it? This is the image, and this is the pre-image. Yeah, so I do the image over the pre-image. That looks like that would be like some sort of like serious like emoji text face or something if you could put fractions in texts effectively. In simplest form, This is 11/40ths, by the way. So it's 11/40th scale is what that would end up being. But all right, we won't do the spider problem today. Thanks for watching, internet friends. Have a good day.